Bien.
Okay, let us begin.
Je vais parler aujourd'hui
Today I'll be speaking about energy-based models, models that allow you to carry out inferences, not just input-output models, but a bit more complicated for more complicated situations, followed by a seminar by Gabriel Sinaif, a researcher at Facebook AI Research, will speak about speech recognition with neural networks and deep learning. 2 points in common with him. He works at Facebook too, and he just landed from New York as I did. So he had a very short night.
Alors donc commençons par
Let us start.
c'est un petit peu ennuyeux ça.
Oh, this is a bit of a problem. Can I get rid of this? Not really.
Bon,
Anyway, we just have to deal with. Oh, here it goes.
l'idée de base des
The basic idea of energy-based systems is for inferences that are a bit more complex than in cases where the system is just supposed to produce a single output from an input. A typical situation is when you want to carry out
de la reconnaissance de la parole,
voice or handwriting recognition or translation, for example, or language models, systems that typically give you a sequence of symbols, for example, that must be structured
et pour lequel
and for which there is not necessarily a single answer. For voice recognition, there are words that you don't understand sometimes, or you may have to produce words that are the right substitutes for what was pronounced. Certainly, for language translation, there are always several translations possible for each sentence in a given language, so there's not one single possible answer for each input. In that case, it's a bit difficult to train a feed-forward network, a network that takes an input and produces a single output, if you have several possible alternatives, and above all, if the output is structured.
alors l'idée de base
The basic idea in energy-based models is that we'll focus just on this module. We could also have a basic module, which is just a deterministic function that takes an input and gives an output. But on top, you'll put an energy-based module. What this module does is that it observes the input coming, well, either directly or from a conventional neural network or any other network, and the output is not a direct output, but it's an input from the module.
il y a possiblement aussi des
Possibly, you could also have latent variables that are not observed,
la valeur aiderait
but the value would help to produce the answer. But we'll disregard this for the time being. We'll just look at this energy-based module as a module with two inputs, one observed and one that must be inferred.
que ce modèle produit
The module produces
une valeur scalaire
a scalar value indicating the compatibility between these two values observed, between the x and y, between the input observed and the output that the system is supposed to produce, leading to an inference. We try to find the value of this variable, minimizing this energy, and would be the result. Instead of having a function
produit directement
directly producing an output from an input, you have the input and output that go in a function, you measure the compatibility, and you make an inference, and you minimize the energy with respect to that variable.
alors c'est beaucoup utilisé
This is very much used under different names in the context of automatic learning for years now. Maybe the first applications of this
le contexte de la reconnaissance de la parole
was in voice recognition, where you really need
chercher parmi
to look amongst all the possible transcriptions to find the one that is the most consistent. So these
d'inférence
inference systems exist in these fields. Very often,
formalisées non
they are formalized not by an energy but by probability. You can always transform energy into probability. The physicists in this room, they understand. You can take the exponential of energy and transform it into a positive way and then normalize it to transform it into a probability distribution. But the approach here to energy is more general. Lots of models use this. Structured perceptrons, conditional Markov fields, and so on. About 10 years ago, I created a long tutorial on this general idea, one way of unifying all of this. But the first model of this sort dates back to a long time ago in speech recognition at the end of the 80s. The use of neural networks for structured learning dates back to the thesis by Botu, Benju, and Hafner back in the 90s. More recently, what is known as graph transformer networks that we use for handwriting recognition, and more recently, structured perceptron, CRF, max margin Markov nets, and so on. They don't use neural networks, but they use more conventional classification systems. Shallow learning, therefore, not deep learning. Here's a prototype of an energy-based system that takes an observed variable x, an input, and the output y is not an output, it's an input as well for the function. The inference function consists in finding the value of y, minimizing this energy function. No learning for the time being. We assume that it is given. For example, to classify images, you'll try all possibilities. You'll give this variable all the possibilities, and you measure the energy you obtain for each value, and you take the minimum. Okay? In this case, animal. As I said earlier, this can apply in many areas, particularly in cases where the object to be produced is structured. To produce an image that is the result of a segmentation, if you want the image to abide by some constraints, you can have that in the energy function. For example, to satisfy the fact that the kernel of a cell is in the cytoplasm, you can do it by hand if you wish. This model is largely used to remove noise in an image. By gradient descent, typically you're looking for an image to minimize energy, which will generally have two terms. One, saying that the image shouldn't be too different from the input image observed, which is noisy, and another term saying that the image must be pretty. It can be learned once again here. As I said before, for handwriting or voice recognition, or for natural language processing, parsing, and the rest. You can always transform energies into probabilities if you like to manipulate probabilities. It's always possible to take these energy functions and to transform them into a joint or a conditional probability. Here, for example, writing a formula to calculate the conditional probability of x knowing y from energy. But energy is a bit more elementary, more fundamental. You can obtain the probabilities from energy. That the opposite is not always true. So you take energy, measuring the compatibility between y and x. You take the exponential, there's a coefficient here that's at random. It's a minus out of convention. The small energies correspond to high probabilities. This convention came from physics, statistical physics. To obtain, well, this gives us a positive number. To obtain a conditional probability that is normalized, you divide all of this by the sum of the integral and all the values of y in a domain. So now if we integrate this with respect to y, we end up with an integral with respect to y above. We have the same term above and below giving us 1. It's as simple as that. By analogy with physics, this is a Gibbs distribution, an inverse temperature, and this term is called the partition function, the normalization term, that is. But in most cases, you don't need to produce probability from energy unless you want to have calibrated scores to calibrate several models together without training them once again. I'll come back to that later on. Very often, energy-based models don't only have two variables, but three. One observed, one that you're supposed to generate, to predict, that is observed in the learning set, but not in the test set. Well, not in real use, that is. Sometimes a latent variable, which I call Z here, variables that are never observed. It sounds mysterious, but I'll tell you more about that later on. For example, let's imagine that you want to train a system for object recognition to detect, let's say, faces. And you have a convolutional network giving you a score, saying if there's a face at each point in the image, applied convolutionally throughout the image, giving you a score map for each place in the image, saying if they think that there's a face there or not. To train such a system, the output is binary, a face or no face. But there's a latent variable, which is the face's position. To train the system, therefore, simultaneously, you must say if there's a face or not, but you must also find where the face is. It's like a latent variable. It's never said by the training set. It doesn't tell you where the face is. It just says that there's a face in the image, and you can see that position as a latent variable. But I'll come back to that. Latent variables may be handled simply by encompassing this model in a bigger box that carries out an inference with respect to Z. So we can write a new energy, which is similar to what physicists called free energy, that depend only on X and Y. And what this box does is that it marginalizes or minimizes with respect to Z. A simple example is minimization. If you take the original NA function, you minimize it with respect to Z, giving you a function that's now only dependent on X and Y. There's another technique, marginalization, which consists in calculating minus the log of the sum of exponentials of energy for all the values of Z. It can be a bit more complicated if Z is a high-dimensional value, giving you another form of free energy. This, from a probabilistic standpoint, corresponds to marginalizing on Z variables, and this is just an inference of the maximum similarity. Let's take a more concrete example for handwriting recognition. We get a word. We're given a word. Let's say we have a heuristic to cut the word into characters. We don't use the method I spoke about the last time. It's a modern model that's the most widely used. It consists in shifting a convolutional network with a sliding window throughout the word. We won't do that here. We'll use a sort of heuristic to segment the word into pieces. Of course, we can't know what chunks go together to form a character before recognizing the character. So you need to have several hypotheses on segmentation, represented here by a graph. On this graph, each path goes through, well, each arc in the graph corresponds to a piece of ink. Let's say a certain set of features in the image. Each path in the graph is such that if you go from the initial node to the final node, you go through all the pieces of ink, the bits of ink, let's say. So we see the complete sequence of all the components of the image in each chunk. The path at the top here corresponds to an extreme segmentation of the word, where you cut up all the pieces, and another path at the bottom, putting together the first two pieces, and another path putting the 3 all alone, the 4, with the 2 pieces of the 4, assemble it, and 2 on its own, which is the correct path in this case. We can apply our preferred convolutional network to each of these components, giving us a score for each of the 10 classes if you want to carry out recognition of handwritten digits, creating a graph with a similar structure, but the arcs are now labeled from 0 to 9 with a score corresponding to the score given by the classifier to this specific category. And now, you need to look in this graph to find the shortest path, the least costly, with the sum of energies along the path is the weakest. And that will give us the answer, in fact. Here is the example I spoke of earlier about face detection. We apply a convolutional network with a sliding window on an input. We tell the system if there's a face or not after training, and the system must infer the position of the face, and it does that by choosing the position where the current score is highest or energy is lowest. A minimization with respect to the latent value Z corresponding to the face's position, giving us a certain flexibility to produce a system where the production of the output is not just a direct calculation but the result of optimization, making the system more powerful and flexible, maybe. One of the first examples combined with neural networks was a system for word recognition produced by Xavier Driancourt and Laurent Boutou in 1991. A paper that unfortunately went by unnoticed, but they were pioneers. For training a neural network with a structured prediction system to recognize words. This is linked to what Gabrielle will tell us in the next seminar. The idea is that you take a sequence of vectors representing the word signal, very often a sequence of vectors where each component indicates the energy in a frequency band. Gabrielle will tell you more. You connect a convolutional network to this. It's a convolutional network carrying out convolutions on time in this case, producing itself a sequence of feature vectors in a way. Of course, if you want to train the system to recognize words, each person can pronounce a word with at different speeds, so the length of words is variable. So this sequence will be variable in length, this one too. The word template, we'll do a classification here to classify words, let's say to recognize spoken words from 0 to 9, a small vocabulary. We need to have a model for each word, and that model for each word must be robust with respect to variations in the speed of pronouncing the word. The way we can do this is relatively classic. This is dynamic time warping, dating back to the 70s in speech recognition, words with a sequence of vectors, but these vectors are not necessarily successive, one after the other. We can stretch out the sequence to align it with the sequence coming here, align it or contract it. As a matter of fact, we can imagine that's a bit similar to a sequence of words where energy corresponding to the period of this sequence of vectors with a specific word template would be the sum of the distances, if you wish, between the output vector here and the in the reference. It's a bit as if you had springs between the vectors. If you pull on it, it increases energy. So for each word template from 0 to 9, we've tried to find how to stretch the springs and the right warping. The position of these variables, well, these are latent variables because we minimize with respect to the position of these vectors to find the match. Time warping, in a way, constitutes the latent variables in this inference. And then we look at the lowest energy. If all these modules, the lowest energy is, let's say, the word 3, or any word chosen for classification. The question now is, how do we train this? A bit more detail here. Once again, this is a classic in word recognition with warping. What's new, or what was new in 1991 was the fact of training a neural network with this type of warping. Warping is very simple to calculate because to find the minimum energy in a system with springs like that, in a single one-dimensional system, is based on the shortest path. You take the sequence of vectors here, the one that you want to match, you try to find the path in a graph, going from this point to that point, and with minimum energy, matching vectors that are closest to each other, and stretching the spring as little as possible. So simply a shortest path algorithm on a graph. How do we train this? The idea is quite simple. In this case, and this is an example, and then I'll move on to a more general situation. Once again, you take the sequence of acoustic vectors, you put it in a convolutional network. Here is a time delay neural net. You recover the sequence of features vector. You have one model for each word, or several, at least one model for each category. You calculate the distance by time warping between this sequence and each model, giving you a minimization with respect to the latent variable. With this time warping, the way you train this is that you need to train the model for the correct word with the closest one possible to the output of the network, and train it with the closest one possible to the output of the correct model template, word template. This is quite simple. You can obtain a gradient of this distance through time warping with respect to the network output, so that you can back-propagate gradients in the network for training. But that's not enough. If you do only that, minimizing the distance between the output of the network and the template, that gives you a simple solution. All templates will go at the same place. The neural network will disregard entirely the input and would produce a constant output equal to all the templates, minimizing the loss function, which consists in minimizing the difference between the correct model template and the network's output. So it won't work. So you need another term in the loss function, pushing back the models that are incorrect. If a template wins, let's say the word 3 is pronounced, and the system recognizes 4. Not only must you bring the output of the model closer to the word 3, but you must move it away from the output of the network. You need at least two terms, one pushing and one pulling, to avoid collapse of all this.
Alors, un petit peu plus de détails sur cette histoire de marginalisation.
More details on marginalization.
Comme j'ai dit tout à l'heure,
As I said earlier, if you have an energy that's a function of three variables, z, y, x, to obtain a conditional distribution with respect to one or several variables, you just have to normalize with respect to the variable to the left, the ones we want to have a normalized distribution. With this integral at the top here, if you integrate with respect to z and y, you obtain 1. So the distribution must be normalized properly. To eliminate this variable z, all you have to do is to integrate here with respect to z. So it's a marginalization with respect to z. And you obtain this formula, but you can realize that's exactly equivalent to using an energy. In this form, if you have an energy that has this shape, and you infer with respect to y, it's as if you took the y here maximizing this probability marginalized on z. This energy is actually a way of eliminating the variable z, probabilistically, let's say. And when beta tends towards infinity, this entire expression converges towards the minimum with respect to z. A simple case, then, of a maximum similarity inference. Now, how do you train an energy-based model? If the system gives us or produces energy that's large, let's say we have a 5-class classification system, so high energy for human, for animal, for airplane, small for car, and large for truck. But the correct answer is animal. The machine, when it trains, must lower the energy for animal and increase energy for car. So that after training, animal should have the lowest energy because the system produces the answer with the lowest energy. So you must train the system so that it gives you the lowest energy to the correct answer and the highest energy to incorrect answers.
Donc on peut voir la fonction de coût qui est...
Now, the loss function is a functional, in fact.
L ici.
Denoted L here.
We
have a family of energy functions parameterized by weights in the neural or the neural networks or the like. These energy functions depend on the input and outputs and on parameters. When the parameters vary, that gives you a family of energy functions, and this is the family where you will choose. The training set is a series of pairs xi, yi, desired input and output, and the loss function L, which is a functional, takes the energy function as an argument, if you wish, and the training set, and you need to find, indirectly we can see this as a W function. What you want to find is a W that minimizes this loss function in a way. But you must design this function so that it does it correctly, giving a low energy to the right answer and high energy to incorrect answers. In general, without any loss of generality, you can write the loss function like this as a sum on average on the training samples of a loss function that will depend on the energy function for all possible x for the x is observed, and will take the desired y and tell us if this loss function will give us the right answer, knowing that the right answer is yi. You can add to this a regularizer that depends on parameters and not on data. In discrete cases here that I've already shown you, as I said, the cost function must push downwards energy for correct answers and upwards for incorrect answers. If the correct answer is here, You must change the parameters in the energy function so that the energy for the correct answer goes down and energy for incorrect answers increases, so that you end up with a profile like this, where the correct answer is a minimum of energy. There are 4 elements to find to train an energy-based machine. First, the architecture for E, containing the neural network, in fact. The inference algorithm to calculate Y from X and the energy function. For a given X producing Y with the lowest energy, it may not be that simple. In the case of discrete categories, it's very simple, but in cases where Y is an image, let's say, it can be quite complex. In the past, people invented lots of methods for approximative minimization, complicated functions in probabilistic inference, but they can be simplified. Next, you need to pick a loss function that will use as an argument the energy function, given it the right shape for each x. And of course, it must be optimized with respect to the parameters. The question is, how can we design the loss function so that it does what you want it to? Let us take an example, a simple example here, a regression example. You take an input, which is a scalar, this variable here, let's call it x, and an output y, this variable here. And you want to train the system. So the blue points, the blue dots are training samples, such that y equals x squared. It's just a parabola. We want to train a neural network to approximate this function. Well, using the energy-based method, you design a machine here. Its energy function calculates the compatibility between x and y. A simple way to do this is to take the output of the neural network, you calculate the distance between the output of this neural network with the input that you give it. And naturally, the best value for this variable is the one that minimizes this distance, and it equals output of the neural network. It's a trivial example, but it's just to give you an illustration. And then you train the neural network to minimize this energy on average in the training set. And here you see an animation of this energy function based on time as training progresses. You start with an energy function that's not very good, and as training improves, progresses, the minimum of energy for each value of x, for a specific value of x, the minimum with respect to y of energy is located around the training sample for that x or around that x. You train a sort of a landscape of energy so that the minimum energy with respect to y is where you want it. This is simply by minimizing the average energy in the training sample. But if you apply the same loss function to this example, we have 2 neural networks, one taking x and one taking y. You compare the outputs. Once again, you calculate the distance between both, a normal one in this case, just the absolute value of the difference. And this is our energy. Here it doesn't work. If you minimize the average energy here, you end up with the problem collapsing, as I said before. Meaning that these 2 networks totally disregard the inputs. Both produce constant outputs. And that will minimize the mean energy but not solve the problem. You end up with an energy function that's flat, and it won't do the job. Leading us to this idea of having a contrastive term, not only a term that pushes energy downwards in our training samples, but can also push upwards energy for incorrect answers. A specific way of doing this, I won't do all the maths, but just to show you the result. This is what we know, in some contexts, as negative log likelihood or maximum mutual information. It has the different names in different contexts. This is the loss function used in logistics when you do log softmax above a neural network for classification. It's exactly this loss function that we use. It tells us as the mean of training examples of energy that the model gives to the correct answer, E of W yxi, for the energy for the correct answer. That will be minimized as much as possible. You take the lowest energy for the correct answer, and there's a contrastive term that is the integral for all possible outputs of E, okay, minus the coefficient energy of this answer. Once again, use sum on all possible answers. If the answer is a discrete variable of a category, this becomes a sum quite simply. Naturally, this sum, well, the log of this exponential sum is a decreasing function of the, so it will push energy upwards. When it's minimized, the higher the value, the more it's exponential. With a minus before it is small, the smaller the integral, minimizing our function if we push all these y's. This is an example of a loss function that pulls energy of correct answers downwards, but pushes energy for incorrect answers as well upwards. This may be obtained from the maximum similarity of all y's in the training set with respect to x. Taking logs and so on, we arrive at this loss function. So that is how it works in practice. In the examples I showed you with the two parallel neural networks, here the loss function pushes the blue dots downwards, but pushes all the rest upwards. So we see in a sort of, it's like you're digging a valley in the energy function. Here's another energy function that is largely used as well in natural language processing, that was used until quite recently. It's known as the structured perceptron. The energy function here is the energy of the correct answer, energy that our model gives to the correct y's, minus the energy of the response produced by the system. If you take the minimum of all on all y's, knowing all the other variables, you obtain the answer that y produces in the system. Is the inference model that minimizes energy with respect to y. So this is the energy for the correct answer, and we try to minimize the difference between both to make this as small as possible and this as big as possible. If the system produces the wrong answer, the energy will be increased for that wrong answer. If it's the right answer, the two terms are then equal and nothing happens. It works. The problem is that there's no margin. It can cause a collapse too with this type of loss function, where all answers actually have the same energy. To combat this problem, we take cost functions that have a margin. Here's an example. A loss function telling us that the energy for the correct answer is as small as possible. This is a square root before it, but that's not necessary. So I push the energy for all, well, for a incorrect response, maybe the most threatening, y bar I here, and we push it so that it is greater than a certain margin m, chosen arbitrarily. That will push the energy upwards until it's at least as big as m. After that, it does nothing with a quadratic cost. Square loss. Here, for example, this is correct with the energy of the training samples remains low and the rest higher energy. The way you choose this y bar is chosen so that it's different from y, I, the correct one, outside a certain sphere, well, above, beyond a certain distance from the correct answer, but with minimum energy. The value of y is the most threatening, if you wish. It's the lowest, but incorrect. There's a whole catalog of cause or loss functions, many different ones proposed by people in speech recognition in particular. They're all based on the idea of having two terms. One term tends to minimize energy for the correct answer, and the other one that pushes upwards incorrect ones. Here's a list. Energy loss is just the mean of energy for the correct answer. This doesn't work. It can lead to a collapse. The question is, can it lead to a collapse? Is stated here. If the margin is 0, you don't impose that has to be greater than 0, in which case it can have a collapse. In this case of the structured perceptron, you can have a collapse, but these other loss functions here are all correct, meaning a margin that forces energy for the incorrect answers to be greater or strictly greater than energy for correct answers. I won't go into the detail on all of this. This is what I spoke of before. In speech recognition, they call it maximum mutual information. In other contexts, it's called negative log likelihood. In other contexts, it's called log softmax, if it's discrete like here. And now let me go into details on how to use this for particular applications. For example, for word recognition, but it also applies to many situations. And you'll see more with Gabriel later on. For those of you who are familiar with graph factors, there's a connection with all of that. A CRF is a sort of factor graph. Well, a factor graph is an energy function composed of a sum. Well, we call them factors. You may think when you speak about factors that you're talking about multiplication. That's true in cases where you manipulate probabilities. But here we're handling energy, which is a sort of log of probability, so the terms are additive. The energy function is a sum of terms. Each term depends on a subset of variables y or z or sometimes x, but that's less important. Each square is a term in the energy function, in the sum. These models, the conditional random field, maximum margin Markov nets, and structured perceptron, are models where you have an observed variable that goes through a features extractor which is fixed, no learning, producing a vector, and this vector, we calculate a weighted sum, the scalar product, with a weight vector giving us a score, energy. Each box does this for a subset, a different subset of variables y. What is this for? Is to produce sequences of y that must abide by a certain structure. Let's imagine that you have a system for language translation here, and x is a sentence in English, let's say, and y should be a sentence in French. Of course, you know the dependencies of the pair of words that must follow each other in French. You know that some words can follow others and others can't. So we can implement this using this term, this factor, which will tell us that you're entitled to put the word, I don't know, black before cat, for example, or square before cat. That's probably unlikely.
Donc ça nous permet
That allows us to impose structures and sequences of symbols. The difference between these models is the loss function used. The CRFs use negative log likelihood, the function I spoke of earlier. Maximum Markov nets use loss functions in hinges, and structured perceptron use the loss function of perceptrons. Learning bears on these weights. So these are shallow models, not deep, because there's only one layer. The energy function is a linear function in the parameters. But there's nothing to prevent us from making these functions more complex. In particular, given that the structure of a neural network or a deep, complicated network, parameterized by parameters that are inside. Our energy function is now a sum of these factors, but each factor is a complete neural network in a way. You can train this with several loss functions, some that I indicated before. These models historically came before these. But people found this too complex. This can be used to do some funny things that can be viewed in different ways. But one way in particular is what we call graph transformer networks. We can see this as multi-layer networks where the state variables are not vectors or tables like in convolutional networks. In a normal network, the internal states, inputs and outputs are vectors. In convolutional networks, they are arrays. With graph transformer networks, GTNs, the internal state of the machine are graphs that are labeled by numerical values, images, vectors, scores, and the like. Each layer in this network transforms a graph into another one. It looks complex, but you can backpropagate through these structures to generalize the notion of neural networks to more complex things. This is the same illustration as what I showed you before, but let me give you an example that's a bit more complex. This is the architecture of a system that my colleagues and I built at Bell Labs in the early 80s, used for a check recognition system. At the end of the 80s, it read a high percentage of checks in the United States, and it was also deployed in ATMs in France for automatic check reading. Modern machines use other recognition systems produced by a French company, but it's quite similar to what I will be presenting here. This was amongst the first systems that were capable of reading handwriting reliably for checks. You take an image, you put it through a heuristic segmenter, which builds this segmentation graph that I spoke of before, where each arc is labeled by a piece of the image so that each path in this graph goes once and only once through all the pieces of ink, if you wish, on the image. Here too, you can separate each of the three pieces here, giving us one path in the graph where you have the 3, the left part, and the right part of 4. Another one with the 3, the left part of 4, and separately the right part of 4, and the correct one with 3 and 4. Each path is an assumption, an interpretation, labeled by the image. You choose you apply your preferred neural network, giving you a score for each category, and you will produce a graph exactly like this one here, where each arc was replaced by 10 arcs. I'm going to put 2 here, and each is labeled by category and the score. It's the energy coming from the neural network. A low value corresponds to a high score, if you wish. And now, the answer that the system will generate is the shortest path in this graph. The path from left to right, where the sum of energy is the lowest. A minimization with respect to a latent variable, a path in the graph. During training, you tell the system that the answer is 3, 4. Amongst all the paths, select the ones whose label is 3 followed by 4. And there are 2 in this graph, this one and that one. And then you take the best of the 2 paths. Here, this one, and the loss will be 0.7, because you have a loss of 0.1, 0.6, giving you a loss of 0.7. So this is the loss, the cost of the correct answer. You force the system to give the correct answer, and it gives you the cost of the correct answer, the energy of the correct answer, and you try to make it as low as possible. Furthermore, we will use a perceptron loss function here. The system will be free to produce the answer that it wants to produce, the one with the lowest energy without any constraints. Of course, the energy that will be produced will be lower than the energy under constraints. This is the energy of the path with the lowest energy. In the previous case, it was energy for the correct answer, which had a lower energy. If energy were the same, the response would be the same. This corresponds to operations on graphs, and what's magical is that you can back-propagate gradients through all of this. If you have a loss function, which is the difference between these 2 losses, not a very good loss function, we need a margin and so on, but just to explain it simply. So we'll calculate a loss function, which is the difference between the energy of the correct answer, the energy that the system gives you when it forces it to produce the correct answer, and the energy spontaneously given, or the smallest possible energy of the entire answer. We can very well calculate the gradient of this difference, which is 0.1 in this case, 0.7 on one side, 0, and you can calculate the difference. It's just 1. 0.7 by delta, this won't move. If you move this 0.6 by delta, this 1 will change by minus delta, giving you a gradient of -1. Since this number is the sum of these 2 numbers, just copy the gradient. In the previous lecture, we saw that if you have a sum operation, when you back propagate, it's just a copy of the gradient. So you can have gradients with respect to the values in these arcs. And here you can have gradients with respect to the values in the arcs copied in the output graph. The others have a gradient of 0. If you change these values slightly, it will have no effect at all on the output. When I say gradient, I should say a subgradient, in fact, because these functions are not differentiable everywhere. They are edges. When a value goes below another one, all of a sudden, one is activated and the other deactivated. So there are edges in these. So technically speaking, it's a subgradient. But once again, you can back-propagate to this here. The arcs that are present on the left receive a gradient of 1. Those on the right receive a gradient of -1, and those that are in both, we do the sum of gradients from the 2 halves, giving us 0. For example, this path, we find it on the left and on the right, and we end up with a gradient of 0, because +1 and -1, add them together, that's 0. This path is correct. It's in the correct answer, but not in the incorrect answer. A gradient +1, these 2 paths, and the incorrect answer, but not in the correct answer, receiving a gradient of -1, giving you gradients, therefore, with respect to the outputs of all these neural networks, that you can back-propagate to the neural networks, several copies of the same neural network showing all the weights. So back-propagating through this, summing up all the gradients to find the gradients with respect to the parameters. The result it will give you is that this neural network will train itself not only to recognize these characters independent of each other, but also to give scores so that this correct segmentation is chosen. And all of this without telling the machine what is the correct segmentation. It's a latent variable. You simply tell the machine, here's the sequence, here's the possible segmentation, here's the correct answer. Find the segmentation that corresponds to the best answer simultaneously. You can call this structured learning or weakly supervised learning. Question. Off mic in the auditorium. Answer. Well, this is the path in this graph. Producing the correct answer, producing the labels 3 and 4. What we did here is that amongst all the paths, we picked the one giving us the answer 3, 4, which is the correct answer. Whereas this one is the path of minimum energy, the shortest path. Well, the path where the sum of energy is the lowest. Possibly incorrect. In this case, incorrect. Comment in the auditorium. C corresponds to constraint. This is the Viterbi graph. We can use the Viterbi algorithm to find the shortest path. And this is the constraint. So we can train, this means that now we can train a system at the level of a word to give the right answer without giving it the exact segmentation of all the characters in the word. That's the principle of structured learning. We can assemble this in systems. There's a general mechanism known as
les transducteurs.
Transducers, graph transducers.
Un ensemble d'opérations.
A set of abstract operations for combining graphs. For example, this is the operation we would need if we had a set of propositions, of interpretations, let's say, of a sequence of written words or spoken words. And you like to combine this with a graph corresponding to a dictionary, a language model. You need to mix these two graphs, saying that amongst all the paths in this graph, I want to pick the one that is in the language. And the combination of those graphs is what we call a composition. And these graphs may be referred to as acceptors or transducers, depending on how they're built. The big question is, how do you build all of these operations on graphs so as to backpropagate gradients to train systems globally? There was a library for this in the Lush system, which is now not much used, and a new one for training networks like this, with graph systems on top, written by Roland Colobert. I think he plans to redistribute it in open source. Well, quite soon. That's what he uses to produce the speech recognition system that Gabriel will be telling you more about. So I'll stop here and give the floor to Gabriel, and I'd like to thank you. We'll keep a few minutes for a Q&A session at the end.